Okay, everyone, and welcome to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and be welcome. If you have any questions, you can post them on Twitter, YouTube, or the Handmade Network forums, and I'll be there to answer. Alright? And as such, let's start with this. Let's open the project. And as you can see here, well, we don't compile, and the reason is that on the build bed have the ML64, we commented the compilation. So if we go to the test asm, this cannot be a thing anymore. So I'm gonna leave it like we got it before, and that's it. So if we go to the disassembler itself, let me open the debugger. Jesus Christ. So I want to see where we left off, because I don't remember. We were disassembling some jump instructions, that's for sure, if I can say it that way. But I don't know if we already disassembled the fire jumps. Probably not. That's the last thing we saw here. So let's see. So this is our current output. Jump R13, REX, jump blah 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 blah, and we have all these jumps are near jumps. That's the basis of it. Some are indirect with the registers, some are direct with the offsets, which are 8 bits, 8 bits or 32 bits, all depends. And that's it. This is on register, this is on memory, and it works the same. So if we go to the ISOM, and we see have the jump, and we got a memory operand let me see the R13 one, which was, so I go there, and we have an FF65, which is not this one, but it's this one. We have 32-bit, and probably it's a 64-bit one. I don't know. Yeah, it's a 64 because we have the 41 here, which extends to. This is the which makes the use of R13, but 41 is 0 1 0 0, and then we have 0 0 0 1. We don't have the W bit set. That means that we have 32-bit operand. So this is a dwarf pointer. So let me copy this. This is a dwarf. And something that probably it's important to start to use the dwarf pointer syntax, so we can just resolve the operand itself, because sometimes it's just kind of bogus. For example, in this case, we didn't know by itself. We needed to see the encoding to see that it was a 32-bit operand size, and we can do that pretty easily if we just add that thing as well, yeah, so let's try to do that as well. So let's try to do that, and we're gonna pass into the fetch memory operand. And right here, whenever we make the push here, first before this part, we want to push another thing here, which is going to be the operand size. And we have the effective operand size, which we can use. So we can just say let me think. And probably it's not even here, because, well, it depends. The rect field is going to tell us, most of the time is the rect field the one that's going to tell us, because the rect field, if you remember, is the one that modifies it. So right here we have this idea that this thing happens here and it modifies the register that we're gonna fetch. And until now that was sufficient for us, because that was the way that we were doing it, so that we present the operand that we need. But now, since this has a tight idea that the fetch that the, how can I say, that the immediate, the register and the memory operand are gonna need. So this is not like register dependent, but is like a context dependent, you know. So this has to be resolved upfront before any fetches onto memory or to the register, you know. So we got the effective operand size being defined at first, and that's important because you know, this is the effective thing, you know. Whenever we pass other stuff, we probably want to do that resolution the sooner we can, so the other stuff can just use it. And that's kind of interesting because if you remember, we were playing around with the effective operand size and stuff, which we finally decided to put in the penalty, like here, and we thought that was the case. But now that we see that we have a match into this, we see that we need a way to, we probably want a variable like this in the context so that everyone can use, you know. So we thought that this effective operand size was just going to be used by the operand, but it's not, you know. It's something that happens to be completely set. And if I say we are gonna, and this effective operand size is not, oh no, this is not, what is this? This is not effective. Can erase all this. And that's it. As such, let's compile. And that's it. Where is it fetch register operand? This one. It uses the motherboard byte and it passes the operand size from there. Okay. So yeah, that's all we want. And such, we have this thing here, and as well we have fetch immediate, which has a similar thing, but it's only on this side. Have a force, and then we'll have the effective thing happening, but probably in the future we're gonna have that kind of stuff. So but we can do it trivially. So I'm gonna pass this on to the, where can we put it? We can do it on get mnemonic itself. I don't see any reason why not to do it, because the mnemonic is the one itself that makes the resolution. So we can just say here, hey, you know, solve that thing. Solve it, well, afterwards probably. And then I can just say that context if you remember, we define those variables to be passed, you know. So we have effective operand size here. No, where is it? Here. Effective operand size here. So it gets passed from get mnemonic entry. So when you say get mnemonic entry on the main call, we have these two variables here, which by themselves we use them. Now the reason why we keep it here is because there's something in here on the fetch memory thing that we don't wanna keep using it, you know. How to say, let's see, I mean, well, we're gonna see the bug whenever we see it, but we want to keep the context now, but we want to keep independence. The only thing, I mean, I remember it was that the fetch memory operand was using this kind of thing, but we already resolved that because we have the effective address size being passed as well, and we have the thing that probably modifies it, which was the thing fetch register open. I mean, it's gonna be the same, I believe. For example, here it uses the effective operand size thing, and but this is gonna be used the context, you know. If we use this fetch register operand, then it's gonna be used in the context. Yeah, and where else do we use effective operand size? This is on the get mnemonic, and that's it. Fetch register operand. We don't use it anymore. So yeah, we are trying to eliminate the effective operand size thing here. Okay, so that's the thing for today. Effective operand size. We go fetch memory operand. We go and say same thing here. Then we have effective operand size, but we don't use it here because we use the effective immediate size, which is right now independent. And in fact, it can also be used, but it doesn't matter. We can just pass the entry, and that's it. So yeah. So if you see here, probably all this stuff is gonna collapse sooner or later whenever we start playing around with all this stuff. Right now I'm gonna leave it here, but in the future you can see the future here and see that it's not stay here too long. Probably it's gonna be moved somewhere else, probably until you get mnemonic or something. And yeah, that's okay. So we can just say we can move this into there probably. I don't see no reason why not. So there you go. So then we collapse that port, and then we can say, well, these are the flags, and we can solve all the bugs. I know but I want to go first to the other ones. There you go here. So here it's just gonna be context for now. And then here we don't need to pass this anymore. You can do that, and then we can do the same here. Fetch memory operand. It's not gonna need none of this. And then here compile. Now this needs it, so I'm gonna pass it like this, and yeah. In fact, we can get rid about this call because we don't need it anymore. We can just use the other, but I'm gonna hold on there. And here you just say this. Where is this? Don't need that. And here, do we pass the context to push displacement? It doesn't have the context, but it doesn't seem why not to do it. Because push displacement issues here and issues in the media, and we just pass the context on both, so yeah, we can just use it. And here we can just say now here the reason that, well, I mean probably we don't need the context, but yeah, I can just say this instead, because yeah, remember that it was because of that special case. Yeah, effective immediate size, effective address size. So yeah, which by itself, I mean, having the context in there probably is not the problem. Well, whatever. And fetch register operand. We need to pass the context here. Context effective operand size. Fetch immediate. If we see here, we see that we have both of them, but we don't use them. So we can just say this. Alright. So now we solve that. Of course, this is not probably gonna work. I don't know. Let me drink some water. It's not gonna work because we haven't done the right stuff. Well, we set it up on the first part and we modify it, but in the get mnemonic right here we say, hey, you know, we're modifying the effective operand size with data size force. In fact, well, probably we don't need this. We want to keep the transcendence. So how can I say it? This doesn't come from the context. I mean, this is not correct. This has to come from the entry. So the entry has a thing that tells us about that, which is all this stuff, you know, immediate size, effective immediate size, register open size, which is this one. It's forced to 64. Then the effective operand size is gonna change to 64-bit, data size 64-bit, data size effective. And if effective operand size is data size effective, we change it to the effective operand size, which now we don't need to do this. No. Okay, I see the problem. Yeah, because since now we're already passing it from this part, you know, we're already getting the right thing, you know. Effective operand size, it doesn't needs it to do, but since the entry has that kind of forcement, that's the only thing we need to do, you know. So right now, I mean, the only case scenario for that thing would be, I mean, instead of doing this, then we have the entry, and the entry uses the effective operand size. So we can just say effective So that's more the thing, you know, data size 64-bit. And if it's effective operand size, then we just use the effective operand size that we already have before, you know. So that's it. So we don't need to do this. You know, we just can't do that, you know. So that's even simpler. And then, so that's the only change. And the others have to use their independent ones, you know. This is the context, and the other sizes are just independent. So we do that. And here we set entry register operand size equal data size operating mode. Okay, we also have this type, so we can do this resolution even before. Let me see if that's okay. Let me put the charger. So this is also another operating mode, you know. Sorry, this one. And this one is used by two instructions, push entry and push entry 1. That's okay. And that's it. This is the only place that it's used. So we can even collapse this a little bit more. And you just say, hey, and you see here we have the same thing here. Well, I'm gonna keep it this way because they are different in essence. So this is okay. So yeah, we just make the resolution as it, and then push register name is used by these two, and it's past the operand size to make the resolution with the big scan reverse. So we can just use the context here. . well. Oh no, sorry, this. There you go. So that's the little change there. We pass this as a pre-pass. I mean, we made it a front so that the resolution is now it's sticky. You know, we have it everywhere. It's the same. So we have to solve all the problems that I don't know if it's, I mean we have the problems that probably we will encounter with this change, but you know it's just a manner of solving it. So yeah, so let's try and see what happens with the stream. You know, let's see what happens here. And let's see the match here, because I have no idea which were the instructions. We have jump dual pointer R15, jump RAX. Now we don't have RAX here. Then we have jump RTOP, push RAX, that's correct. Move SPL RAX, move RBX. We don't have the RBXs here. That's interesting. And we don't have none of them. We have RAX, R13, RAX times 2, RBP, RAX times 2, RIP, RAX times 1, FF0, RAX times 4, 0, 0, 2, 2, 2, 2, 1, 1, 0, RSP plus R12 times A, RBP, we don't have RBP, nor R8, R12, R13, RAX, move RAX, RDX, we don't have that one, none of them. Add by pointer RAX plus FF0 OB, F add ST0 ST1, FUCOM ST1 ST0, FLD 0004, PM resume, PLIN R, X70, X71, shift left double, dual pointer EAX, we don't have EAX there, and we don't have EAX there. So it seems that all our register operands seems busted because of that, and that's okay. So let's go one by one. You know, we can start with the jump RAX here, which is a simple one. So let's go and rewind here. I can put breakpoint there. I don't know which was the string, but we can see FFE9, is that it? Probably it is. E0, sorry. So FFE0. So it's gonna be the first one, so well, we can just do it. Whatever. So this is gonna be that. now the breakpoint is not in the place. There you go. And this is, oh, we already disassembled jump everything, but it has the same FF. Oh, because yeah, it has the prefix. Okay, okay. My bad. Yeah, good. So this is the second instruction, which is jump RAX. So let's see what happens. So we begin the thing here, and we say effective operand size and effective address size is gonna be operand size for 8, the normal stuff for 64-bit mode, and then well, it's mandatory REX. We don't have any REX. Then we have this stuff. We just assert this stuff, and we just try to get a thing. I'm gonna put breakpoint out here. I'm gonna just say hey, continue. I don't care about that. And the entry itself, it's a jump instruction, that's correct. And the entry register operand size is well, we don't know, but oh, it's 464. That means that the effective operand size is gonna change to 64-bit mode. Okay. So we can even see it here. There you go. There you go. And then there you go. We don't have that. Moderating byte. Moderating byte is going to be E0. That's correct. Return the result. Fetch the memory operand, and it's going to be a register. We have a context effective operand size, which is 8, and we enter here and register operand size. Oh, here we we still happen to have that, you know, which is not the thing anymore. So let's, yeah, that's the problem. It's just what's going on here. What's going on here? So we forgot that here. So in fact, well, you see here, fetch register operand, the main use of it is not anymore used because we already pre-passed that stuff. So we can just get rid of this call and make so the only reason that we are sticking this, the only reason, how can I say, the only thing that it's as an impediment to get rid of that is just this up count, because if you remember, we have the up count so that we can get rid of that, but we probably can get rid of this as well because we don't need to have that thing. It's one of the simplest ways to do it. That's the only thing, isn't it? So we have to try to find out where does the up count. It happens here. And it happens here. But we only check it here, which is kind of weird. So we cannot do it here because remember that this is a multi-purpose thing. So well, let's just first I'm gonna just do this in the way that we were doing it before. Context, operand size, effective operand size. And then the next step, once we solve that, I'm gonna get rid of the of this call, yeah. If we want to. If we don't want to, whatever. So this system stay. What's the problem here? And here we don't need this anymore. There we go. So let's see what happens now. So this is the thing. Let's see what happens. What happens? You know, we have an effective operand size of 4. Oh yeah, my bad. I was like, now we have an operand size of 8. We have an I byte count of 1. Fetch the memory operand. We have this. We say, hey, you know, pass it on, fetch it, whatever, and if flags fetch mother and byte, make offset selection with the context. Selection offset selection regroup. And the register name is a buffer is RAX, which is correct. So we have jump RAX, and then let's go for the other ones. The other one was that, so that's not going to be a problem. So let's see now what happens. We have RAX back 0015. Let's just make the match. door pointer R13, jump RAX, jump of 115, jump FFFF8, push R12, push RAX, move SPL RAX. This is a problem here. Move SPL, we have move ESP. This is move RBX, R13, RAX times 2, 0, 0. Then we have move RBX, RBP, RAX times 2, move RBX, RBP, RAX times 1, FFFFF, move RBX, RAX times 4 plus 0, 0, 3, 2, 2, 2, 2, 2, 1, 1, 0, 0. Move RBP, RSP plus R12 times 8, R8, R12, R8, R13, R8, RAX, R8D, RAX, 0, 3, 2, 2, 2, 2, 2, 1, 1, 1, 0. Move RAX, RDX, that's correct. Add RAX, FFFF0, OP, ST0, ST1, ST1, ST0, O4, being resumed. EX03, EX door pointer 0, 0, 0, 0. So now the only thing that's missing is this ESP, SPL, which has to do with the shifting back, you know. So let's see why we have that, which in fact I can even try to find it here because it's just simple. So we can just try to find push register name. I think it was there. It was here. We have the RAX byte info offset, selection offset plus equal 4, I don't know really. This is the operand size, and this is the thing that happens to make that bit shift, which by itself I don't see any matching with the operand size itself. Yeah. So let's see what happens if we rerun this, and the one is this one, so is 1, 2, 3, 4, 5, 6, 7, the 7 instruction. Six, 7, so we have 48A20. That means that is it this one? Probably it is. This is a push. So yeah, this is the thing. So we can just say so there you go. There we go. Is it the thing? Push RAX, that's correct. So let's see what happens. You know, it has to be the register operand. The problem here, we have a context there. We can just see how it works for 8. The same thing here. we have an REX, so it doesn't modify anything at all. And get the mnemonic, and I'm gonna just put a breakpoint here. Oh my god, there we go. It doesn't happen to modify anything, so we just move around. First we're gonna go for the memory one, which is a memory thing, and this is correct. We don't have anything weird going on here. Push string to buffer, and the buffer is now REX, and that's correct. Now fetch register open. Let's see what happens. We have the result. We have a context with the effective operand size of 4, so that means that we should have it. So selection rect type is GPR. That's correct. We make the offset selection. We unfetch the RM field, and the offset is 4. So whenever we push the register name, we push it with 4. So that means that if I say pushing, we shift for the info, let me put it here. We have the offset of 2. So the offset is not gonna be moved because of the operand size. Now how was this done? It has to be 0, and the offset is 4. That's correct. So selection offset is 4, and the info offset so isn't that weird? Because SPL shouldn't be GPR, you know? Should remember on the registers we have this, yeah, I mean we still have to work with that thing, but you know, we have SPL, BPL, SIL, and DIL are like another group, you know. They don't are nor GPR nor GPR64, which are these groups that we set up here. So we don't have to bit scan reverse to set the row, because the row is always gonna be this thing, you know. The others are just the same. Well, these are not joined together. We can just do that. This as well. None of these are done. Have to be done independently. You know, it's just that because we have SPL, so the entry is the problem here. Or at least that's what we can see. The entry has register type that is GPR for this instruction. Well, I mean, in this, yeah, and it cannot be changed because it doesn't make any sense. So, yeah, using SPL is just bogus. So how we were doing this before? I mean, how was this working? Because it was making the assumption that the rect type was passed correctly. Like, oh, we're gonna go and get that because the info offset, the selection rect group type that we pass from the, if you go upper on the call stack, we say, um, the selection that we modify here, it has to be GPR right here. We just say, selection rec group rec type 64, but ideally this should be done here as well, or somewhere before, not here in line, because yeah, here's not gonna enter and it's not gonna happen. So the one that solves that is the register name, or at least that's what we, let me see. We have make offset selection, and let me see the table because it's a table that I want to care about. Right now it's on the mod RAM, so it's on the 32-bit, and we are going, let me see the opcode byte so I can be sure. So I'm sorry, it has to be 20 is the opcode byte, is the mod RAM byte, sorry. So 20 is this, is EAX, which is RAX because of the RAX prefix, and we have this, which is ESP, and we want to use SPL, which is the lowest bar, and SPL, I don't remember, but SPL BPL could, I don't remember, let me find it. I don't remember which was the usage case for this. SPL x86. I don't know if I have it. No. So no, this is not. We can find. I know where to find it. We can go. No, it's not here. It's not here. It's here. No. Here. No. Here. Right here. For using SPL, we need REX prefix. Oh, so that was the reason we needed REX prefix. And we need REXP. So that's why we have a byte register. So we're moving this instruction. It's yeah, it's totally buggy, so we have to change that. Let me see. No, on this assembly, here you go. So we have a move SPL, you know, where it's pretty much saying byte pointer at Rex, move it to SPL. So in the test asm, we have that thing. Yeah, we have SPL byte pointer. So let's see the encoding. So let's see if we don't have any problems with that, because it seems like it needs REXP, but we seem not to have that thing in there. So I'm gonna say vc test PL there, and I'm gonna delete test as and I'm gonna delete test as then I'm gonna generate it back, then and say that ml there you go. So I can just say dumping this as bytes. Boom. So we have for the SPL, here you go. We have move SPL byte pointer REX, which is 488820. So if you see, there's no base pointer, which is kind of weird. It's just with the REX prefix that it solves, make the solution. This is the main byte, which makes a for a move, and the 20 is the mother byte, which selects REX and selects SPL as well. So how to say it? How to say it? Well, that seems fine. So right here, whenever we fetch the mother, let me see. Let me see where it should be happening, because on the push register name we see that is not like the thing at all. The bit scan reversing parallelity is a thing, but the solution should be done before, you know, like, oh, you know what's gonna happen, it should happen before the selection rec group. we have an REX byte. So how can I make sure that, let me go to test asm and say that I have move SP like that, same stuff, and this is like that. If I see the decoding, I can see now we have 8B 20, so it changes totally. So we have to see the encoding for 8A20. So let's try to find here. Here we go. So we have we care about 8A. This one, these two, both of them work with with A. The other is 8B. That's why this works with 16 and 32. Yeah, so that's the reason it changed. We have, this is valid in 64-bit mode. If we move register memory 8 to register 8, and that's the thing we have. So yeah, I mean, it's totally valid. It's not something bogus that we invented. RM register memory valid, inix rex, that's all she needs. That's the reason why it was working. That's why you have 40, and that's why we don't have 41. Just kind of weird, but yeah, we have. I don't know. That's not kind of thing, but we have 8A. And this is, does this mean it's an extension? Oh, okay, okay. I was like, what's that? In 64 mode, RNA cannot be encoded because the following byte registers if REX prefix is used: AH, BH, CH, or DH. So that's correct, but we can use SPL. So that means that if we have this, that's not possible. Or at least, well, it's not possible with an REX, but it's not gonna put the REX, I guess. So yeah, look at this. We don't have REX because we kind of use REX to have that. That means that we have to have this way of doing it. So what's the purpose of the? So you need, yeah, because you need REX to so they're pretty much the same, you know. I mean, they're the same. The only thing is that one can use REX and the other cannot. You know, it's just like, oh, we have REX thing. So that means that we cannot use nor in RM8 nor in R8 we can use AH, BH or whatever. We need to use them here. So when we say to 0 on the mother M, we are using this one. We are using REX here and we're using whatever is here. But it has to be so the encoding itself, you know, the problem is from encoding, you know, because we know that 8A by itself is 8-bit, you know, that's for sure. So we can just get it solved from there and then make the up solution afterwards. So we know for sure that it's gonna be 8-bit, you know. We just have to make sure which one it is, you know. So we can just say this. Init so we have a move. I don't know which move it is. We have to make sure which one it is. So let's see. We have to have is 8A. This is the only one with 8A. We have an 8B. So it's this one. So it's the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's the 6th. One, two, three, four, five, 6 is a move O2 entry. So this is, oh yeah, we have data size 8-bit. We have set it there. We have it there. And but we're using the register type, which is not defined. So this is correct, you know. the thing is that we are not using it, and that's why, for example, this we have to use it. That's the problem. Well, we have to use it, and we have to solve all other things. So my bad, my bad. So as well, test as where is it? Well, mm, let me think about this. We can do it that way. So that's the first one. We have to make sure that we use it. And the next one is, now that we solved that, we can start by saying we have ones that have invalid ones. So yeah, probably we want to use that as well. Yeah, that's okay. We're gonna do this. So for first thing, well, that's the first thing we need to use it. And then on the fetch mnemonic entry and the place where no fetch register operand, sorry, and the place where we use this stuff, I want to say that this thing is not gonna be there. Okay, so we here we make the object selection here as well. So we can just trivially put it on the other side. And say that, well, that would solve it. I believe. I don't know. Info offset is gonna be 0, selection offset is gonna be 4, we know that. And the context rex by it's present, so yeah. Now I don't know if we wanna keep it here, but yeah, I'm gonna keep it there, whatever. There we go. I push rex. We have a 1 byte thing. We have rex. And the yeah, it's gonna get well, it's gonna yeah, because we're using the operand size. That's the thing. But the type is not. Yeah, it's correct and it's GPR, but yeah, it's kind of weird. It's kind of weird. It's kind of weird the way we use it. Yeah, I mean, yeah, I mean, we are just like inlining this stuff. but we don't have a. I mean, if we push it, we have a buffer. We have SPL now. Yeah. So let's see the match. R14, RAX 15, FFFF8, push R12, push RAX, SPL, RAX, RBX, R14, RAX times 2, 0, 0, 0, RBX, RBP, RAX times 2, 0, 0, 0, RBX, RBP, RAX times 1, FFFFF, RBX, RAX times 4, 033222110, RSP plus R8, R12 times 8, there you go, R8 core pointer, R12, R8, R14, R8, RAX plus displacement, RAD, RAX plus displacement, RAX, RDX, RAX, FFFOP, FN, ST0, ST1, FCOM, ST1, ST0, FLD04, then resume, PLNR, XM0, XM108, shift left double AX03 at AX displacement. So yeah, I mean that's it. So now with that change, it, we can just try to try. I would like to think about eliminating that call, fetch register, this one, because we don't need it anymore now that we put it back into the place where we should be. And then yeah, so the only thing that we have to think about is the context up count. So I want to see what happens just for now. What happens if we do this? I want to see where does the problems appear. Now here we have to pass the context of brand size. Here the same. So we can see where do we find the problems? Alright? So for, for example, well, let's see the match. I already see that one problem is that here RSP RAX what else? RSP RAX, O15, FFF8, R12 RAX, SPL by pointer RAX, RBX R13 RAX times 2, RBX RP RAX times 2, RBP RAX times 1 RBX, RBX RAX times 4, O332110, RBP RSP R12 times 8, RA R12, RA R13, R8, RAX plus 0.21100, RAD RAX plus the same by pointer ST0 ST1, FUCOM ST1 ST0, FLD SPLA, Vim resume, so it seems like the only problem is with one instruction. Even these R12s, RAX, they don't have the problem. So let's go and jump to that instruction with RAX and see what's happening. For that, we just need to put this back. There you go. So let's see what happens here. We begin the context. It's gonna be something. iBase is FF, that's correct. We have an REX, let's see what happens inside. I'm gonna move towards here. So here on the context we have an 8-8 thing here, okay. So then we have a fetch memory operand, which by itself we don't have a memory operand, but we're gonna go anyway and do it. Because the operand size is valid. So this is correct because it's gonna push RAX, that's correct. and then whenever we fetch the register operand, the entry itself tells me that the operand count is 1. So we didn't modify the up count in that part. Oh no, because now we set it right there. Yeah, we just do it on the fetch memory operand on the side of the memory, you see? That's kind of buggy, isn't it? So right here, yeah, here's the countable sub count, and it just happens in the side of the memory. So if we do it for both, something like this, then we didn't need that problem. But so if you see there, we probably don't need to we can do that, and then we can say here that we don't fetch a register operand, you know. Instead, we just fetch a memory operand, which we can call fetch operands, and then the media I'm gonna leave it like that, but and the flags are gonna be the problem. What are the flags used? And if we do it that way, then we can just say where we see flags, and my question is, the media needs the flags? No flags on media. The instruction doesn't need the flags, and the get the money does need the flags. Let's see what for. So they are totally independent, isn't it? We can just say fly the cooler flags. And if we do it that way, we don't need this anymore. And then we can just compile that. And here I'm gonna make the solution by copying this thing. We don't need this anymore because this is the only place that we use it. And we just do that, and then we just do that, then we just do that, and then that probably means I'm gonna leave it like that right now, but then I'm gonna just get rid of the flags because we don't need it anymore. Rec buffer cam. This is gonna be another buffer. Well, we can just pass it, I guess. Rec buffer. For now, I'm just gonna do it that way. Probably as well, we're gonna just make the collapse of everything here. There's no need to do anything else. Do, 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 do. so I see where everything is going. I'm not gonna do the change right now. I just wanna make the solution, which I'm just gonna say now since we did it that way, that means that in fetch operands, whenever we do this, we want to make sure that it just happens with the operand size. With the that we don't need the up count. That's the whole point. So that we were doing it here, but we were trying to get rid of it. So this is not like this. Even better, you know, we can just do it. We can just do it this way. That's what we want to do. And then, which it would be the same as before. And then this is true, which is the case. Yeah. So we don't need this. here. And that's it. That's what I was just thinking about. It's like, well, I'm just gonna do everything. And so what was the problem? It was the RAX, isn't it? So now we have that. Let's see the match. Let's see the match. Into EagleFly disaster. Yeah, right here. Mm, so yeah, that's correct. Yeah, we got it back. So now, with all this, this fetch open stuff now is the thing that we wanted it to be, which is the only call that we need. Well, and with the immediate and stuff. So, I mean, one way to think about this is just to copy all this stuff and get rid of this call, if that's what we want to do. Which I know, I know for sure. I don't know for sure. Um, but then I mean we got rid about the notion of liber. I mean, this is simpler because we don't need to care about where to do the fetcher. Now, of course, that makes this call unusable. Fetch register operand. We don't need that anymore because that was just not the case. We don't need that. This thing just gone because, well, it's because it also fetches that one. But if I say, look at that, we don't have it, so that's it. That's good. So we just get rid about that. You compile. And we have the same stuff, So that's perfect. So now we just have one call and that's it. We can even collapse the immediate stuff. But I think I'm gonna leave it like that, yeah. Yeah. And then what I'm gonna do, so now let's add the stuff that we wanted to add at the first place, which is the pointer stuff. And we can do that pretty easily. You can go to fetch operands, and since we already know the operand size since the beginning, we can just add it in here, So now we don't care about that and just say, oh no, I'm gonna just add it. And I'm gonna put it in line here for now. Do we have it in yeah, we have it here. And for doing this, I mean, we can do something totally independent for this, but I was just having the idea, like, I mean, the register types that we can probably link them and just have the same data information for both, because ideally we just want to fetch the thing once and not use it all the time, so per example, when we use fetch register operand, now that we only use that call, which is nice. We have an object selection, that happens to be, this is the thing that selects it, this is the thing that we use right now. We pass a selection thing, and the selection uses GPR64 if that's the case. If not, we just use whatever we try to find out, and as such, we use the rex to define the type. So I'm gonna inline it right now. Probably we're gonna see the thing. Yeah, I'm gonna do the stupidest thing possible. So I don't know if we have S words and something like that in assembly language. Let me see. We have an S word. That's correct. Okay. So yeah, we have S word. So let's see what happens now. I have no idea. I have no idea. For example, the first instruction is a memory one. So we have on the context that we have 88. Is that correct? Is that correct? I thought it was. Oh no, yeah, it has to be chord because we are jumping to an offset. You know, we need a pointer there. So yeah, it has to be chord. My bad. My bad. So we initialize the data types. We see the info. We have an offset of 3, and the type is chord. That's correct. And there you go. There you go, chord pointer. That doesn't need anything. Byte pointer, chord pointer, chord pointer, chord pointer, chord pointer. All these are chord pointer. This is a byte pointer. This is chord pointer as well. This is a door pointer. This is a chord pointer. This is a byte pointer. I don't remember. Probably it is. This is a byte pointer. Nah, this gonna be a byte pointer. It's gonna be byte pointer. This is door pointer, door pointer. So let's check that out. The FLD instruction should load as a floating point one, you know. So it's not nor a chord pointer nor anything, but it's just like. In fact, I don't know how does the disassembler does that. How do they do it? Do we have that? It's a chord pointer. DDO5 B2F00. That's the instruction we have. No, we have DD0504. Well, yeah, well, it's the same because this is the displacement that we get. So yeah, it's the same instruction. It's just simplify. So yeah, this is instruction, and this is telling me that we have a chord pointer. Well, that makes sense, isn't it? Because it has to be. I don't know if this is the double one. already double extended, so we have to find it out. Let's see. There you go. So yeah, it's 64. So it has to be core pointer. So the problem is, yeah, we are missing on the entry there. FLD, because the other H1 is different, D9, DD, DB. So DD is M64. FLD, there you go. And this has to be do we have real thing? 64-bit. You can leave it like that. And the other one that I was thinking about is this add instruction, because is the add with extension table. We have I don't know, what do we have there. Let's find it out, because yeah, as we carry, here we go, and the one we care about, do we have it here? I don't know. Here we go. Is it this one? It has, oh yeah, it is by pointer. Well, I don't know, 80 80 10 40 80 80 10 right here. We have I don't know if it's this one. It should be this one, isn't it? 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. Yeah, so this is 80 40 OXF0 80 40 80 40. Okay, this one we don't have RBX. That means that is immediate 8 to register memory 8. So yeah, that's the reason why it's a byte pointer. That's correct. So in the entry, which should be this right here, we have an immediate size of data size byte, and I don't know why do we have invalid thing here, or how do we found out? Oh, it's because it's the same, because it's invalid. The invalid value is the same, so this should be like this. I believe. Let's see. And this is an extended. Well, this is I can say I can call it 64. No, okay, data size 464. It's not that it's forced, but you know, it's just keep it 64. Yeah. No, it's not 464 because RM8 is still RMA. It's just that it's an extended in A. So this is not like that. This is 8-bit. Yeah. If it's an extended or not, that's because of the REX. But it shouldn't be, because why would you sign extend a register memory? It has a dot there, so let's see the dot. So yeah, you gonna use AHPH. That we know that. But what's the case of sign extending if the register is 8 bits and the immediate is the same size? You know what's going on here? It should be the same, I guess. Now the thing, yeah, because there's no difference between in the data size, operand size stuff. Or not, you know. So yeah, this is correct. It's an 8-bit thing. We have any media size that's blah, and we don't have. We can sign extended if we wanted to. So this should be, how is called this stuff? Effective in media size. Yeah. It depends on REX. .64. I don't know how to say. Well, I'm gonna leave it at that. But yeah, the reason that it worked is not that we use it, but it's just that the operand size is the same, 0 or 1. It's gonna just keep in 0. Um, is this gonna change anything? I mean, Well, we're gonna keep it invalid, I guess. Because right now we don't have a way to defer that. But yeah, because how to say it? This is a special case. We have to have a better way to say if we have a register or if we don't or whatever. Because on the abstention tables we don't have a rec field. That means that we just have the mother m. The mother m, we are fetching it and we're getting the operand from there, and then we should make sure that on fetch memory operand here we don't do it if the rec field is occupied or something, you know, like if rec field, I'm gonna put it here. Because the sizes now it cannot be definitive anymore, because now we are transitioning to use the sizes, effective operand sizes, to be important, you know, to be not a decisive thing here. So we have to make some changes there. But if I leave it like that, it's just gonna work for now. Where is it? I have to close this. So there you go, by pointer, core pointer. Then there you go, we have a core pointer now here. That's correct. Dword by pointer, dword core byte cord. And if we want to be fancy, we can just put some padding onto it. Well, I don't know if I want to do it that way. What I want to do, let's call this how you call it, it was printf. I don't remember the name. Where is it? It's been printed, this one. So we will need to I'm gonna do this. So we can do it that way. And there you go. And now we have indentation, some spacing with the right types, so we match the operands whenever we want to, and I think that's nice. Yeah. So yeah, so I think that's it. We still have to make a bunch of work in the code because we are happening to do it in the way that we shouldn't. So we have to make a cleanup here and find out, and define how do we want to use each data information, because you see here effective operand size, we have make the change to use it as a context thing, so that we want to keep it that way now, and we want to make get rid of the operand count, which for now it's okay. We get rid of the function call, but we haven't rid of the up count, so we still have to make this thing here. So yeah, so we don't want to we want to get rid about this, let me put it here to do get rid of this, and that's actually this is the same here, like that. So that's the next thing we're gonna do, and that's it. So if we run it here, and that's our disassembler. Look at that, we have a disassembler. And yeah, oh no, oh, it's because we didn't pass it. Okay, but we didn't use it, so that's okay. I was like, what? Yeah. Yeah, so we can just pass blah. And yeah, and yeah, so this is getting form, you know, this is looking like an assembler file, which is the thing we want to do. And yeah, so yeah, I don't know how many times I have to say that word, but please, you have any questions, post them on Twitter or YouTube, and I'll be there for you to answer all your questions you may ask, with the consideration of being relative to the recording, that you know that the recordings and the question match, you know, so that the stream, you know, make the question related to the stream that we made that day, and I'll be happy to answer them. Okay, with that said, I would say thank you very much for coming, and I will see you on the next stream. Take care.